Hey guys, Max here. We've been doing a lot of talking on this channel about different parts of the AI infrastructure market. We've been talking about common parallelization strategies. We've been doing a little finance talk, a little econ talk. But I want to do a video that basically starts off the series talking about what we're doing as a company at Tandem and how we're approaching all the things that we talk about. So at the core of Tandem, to those who don't know, is a fully open source research lab working on cluster level GPU orchestration across multi-cloud heterogeneous hardware. So at the core, we have a governing algorithm that basically looks at your fleet, looks at the jobs that are happening on that fleet, and decides not only the placement, but the configuration of hardware and software used per job for every single job. So this is going to be a very high level introduction of the algorithm. We're going to go more in depth as the videos progress. But at the core of this algorithm is we have something called a directed acyclic graph, a DAG. And what this means is it maps a relationship between three types of variables. We denote them as x's, v's, and y's. So for this video, I'm just going to focus on the x's, but let me tell you a little bit about what each of these variables represent and why we actually chose this structure to build the algorithm on top of. So x's, in this case, are all the variables that you as an inference team are able to manually tweak. So we're going to go fully into this, but these are the parallelism strategies that you use. These are the engines that you use. These are the sizes of the batches. These are all the things that you yourself manually configure when you go and deploy some sort of model on your hardware. Now, the V's are actually the intermittent physical qualities that we as engineers are able to observe but cannot directly tweak. We'll go more in depth in the next video about what these V's are, but as an example, it could be the kV pressure inside the hardware. It could be pipeline bubbles in the GPUs. It could be if you're doing disaggregated serving, the ratio between prefill and decode machines that you have running a certain model. So these are all the intermediate physical qualities that go into model deployment that we can observe but cannot directly tweak ourselves. These are latent variables that are a byproduct of the x's that we are able to tweak. And finally, y's are business outcomes. So when you deploy a model, right, you want to achieve some sort of business outcome. Financially, this could be dollar per token. In latency, this could be your throughput. This could be, the tokens per second. Anything that's an observable outcome that you want to get out of a model deployment. You can imagine why we decided to go with this sort of structure, because you can't really go directly from an X right to a Y, right? You can't say that changing a type of parallelism strategy will directly affect your throughput, for example, because there's a whole intermediate column V, which is the actual physical qualities happening inside the hardware that will affect this. That's why we label it as a 3-node DAG. So, okay. V's and Y's will be covered in the following 2 videos, so let's only focus on X's. The goal here, and I only have so much whiteboard space and the ability to write this all out, but the goal here is to kind of show that the parameter space is massive. I only drew up maybe, 15 to 20 different variables, but truly the parameter space of what you could actually change is 150 at least. So let's just go through all the things that I have here. You have all your parallelism strategies. So how do you actually take the model that you have and distribute the model across the hardware that you own? The size of large language models now, especially the frontier intelligence ones, are so large, they simply do not fit on a single GPU. So how do you actually take a single model and divide the computations within each layer across hardware? So that's parallelism. There are 6 main types. So you have tensor, pipeline, data, context, expert, and sequence. Forgot the expert part. And you don't only have 6 here, because within each type of parallelism, there's also the degrees that you could parallelize to. So for example, tensor parallelism splits the computations in a given layer, but that has various degrees. You can have TP1, TP2, TP4, TP8. Usually 8 is the max, right? Because you want to stay in a single node. But that applies to every single one of the 6. So now if you think about all the permutations and combinations that you could make, just inside the parallelism column, that's already much, much more than 6, right? Then you also have to consider, okay, what is the actual engine on top of the GPU that's running this workload? The names, you have VLLM, TensorRT, SGLang, right? These are all choices that you could use. But then within each type of engine, you have its version, right? So different versions, for example, of VLLM 0.10 will perform differently, than a previous version of the same sort of engine. So within these two, you also have some sort of choices that you need to make, right? So we're just 2 in, but you can already see, the parameter space is growing pretty fast. Okay. Now let's think about your batching and your routing of actual requests. What is the sequence number that you're using? What is the batching policy? If you have multiple replicas, how are you handling the routing as requests come in to every replica that you have, right? So add these, and your parameter space has increased even more. Okay, now let's look at all your memory and KV cache. What's your memory utilization of the GPU? Are you using any prefix caching, right? Are you doing a chunked prefill? How are you managing your KV between the machines that you have? Okay, that's even more stuff you have to worry about. Now let's look at the model. Are you using the model just as it is, or are you quantizing the model, right? Are you quantizing the model? You could even quantize the memory transfer between each of the pieces of GPUs that you have. Okay, that's even more things to consider. There's a concept of PD, prefill, decode, disaggregation, right? There are 2 main operations when you're dealing with inference. Prefill is you take in all the context that's provided to the model, your user request, all the context that you have in your chat, and you have to take it in and you have to develop your KV, your key value, your key value. Okay, that happens during prefill, and now you actually have to go and generate the request. That's decode, right? You have to auto-regressively generate the output token by token. These 2 have very different physical requirements. For example, as opposed to prefill, decode is memory bandwidth bound, because if you think about it, it's auto-regressively producing the output token by token. So the type of machine actually used for prefill and decode is different. And the requests and the configurations for each machine are also different. So now you have to think about, okay, if I have a cluster of 10 GPUs per se, how do I split that cluster of 10 and partition it between prefill and decode? What's my prefill count? What's my decode count? Do I even enable it? For every type of prefill or decode, what's the GPU type that I'm actually using? That's another set of parameters that you have to consider. For brevity, I'm going to keep this video short, so I'm not going to expand on all of this. But the list goes on and on and on. And you see that within every single type of variable, there are increasing number of degrees to which you could, configure within that variable itself. So when you kind of stop and you think about this, you see that the parameter space is massive. And quite frankly, an engineer cannot do this manually. It's simply impossible. If you put your head down and you know kind of the type of model that you have, and you have a general idea of, the workload that's happening, maybe, in a few weeks, you can find some sort of configuration that works, but manually to go through every single one of the combinations that you could create just within the X column is impossible. And that's what we're trying to do. We're trying to have a single cohesive algorithm that looks at all of this. And in the next few videos, we'll talk about how it relates to the V's and the Y's and goes through and optimizes in a joint optimization problem. How do you optimize a certain business outcome to not only focus on, let's say, this part and this part, but how do you take into account every single one of the variables that you are able to tweak to achieve some sort of business outcome, such as dollar per token. Again, this was meant to be just an overview and kind of an explanation and illustration of the scale that we're talking about here. This wasn't meant to be any sort of technical deep dive as to what each of these are, but I think laying them out like this, and especially thinking about the degree that happens within each variable, kind of gives a really good picture how grand this space is. So thank you for watching. Stay tuned. In the next video, we're going to be talking about V's, and we're going to explain how the X's and